Welcome, students, to our virtual lesson. Today, we are in chapter 13.3, the nature of solids. So we start off with a case file study here. What is the strongest material in the world? When you think about that, you might say something like a diamond. Perhaps you might say titanium or platinum, which is the hardest metal that we know of. But believe it or not, it's actually a non-metal structure made out of carbon. Well, we know that diamond's made out of carbon, but these are called Buckminster fullerenes. And you can see an example. It's called fullerene nanotubes. This is nanotechnology, which is microscopic technology. But this is made out of 60 carbons that are bonded together in 20 hexagons and 12 pentagons. It is said to be the hardest known substance because of the arrangements that these atoms take. So the model for solids, how are the structure and the properties of solids related? And that's what we're going to get into here. First off, a couple of things. When we talk about a solid, we realize that it's dense. It's very dense, and it is compressed. You can't take a solid under normal means and crush it any smaller than what it is. That is because its particles, its atoms, its ions are arranged in such a way that they are rigid. They're in a locked position and they vibrate in that fixed position. And that's what this is talking about right here. They're vibrating around a fixed point. So solids do not flow. Solids have a definite shape and a definite volume. So when we talk about a solid, realizing that we could heat a solid, and if we can apply enough heat so that the particles begin to vibrate more and more with kinetic energy, it's kinetic energy, it can overcome the attraction and begin to flow. And that is when you have a liquid state. And so the melting point here is a vocab word for you to get into your notes. Melting point is the temperature at which a solid changes into a liquid. At this temperature, the vibrations are strong enough to overcome the attraction that keeps them in that fixed position, and now it has flow. Remember what flow means. The particles, the molecules can flow and move past one another. They're no longer in a rigid fixed position. So now we have freezing point. Freezing point, another definition, is the temperature at which a liquid changes into a solid. And here we go again, another one for your notes, freezing point. Here's a very big concept. Sometimes it's a little hard to understand, but I'm going to put a little mark here. The melting and the freezing point are the same temperature. The same temperature. Put a little exclamation point there. Think about what's happening. They're in a state of equilibrium, and that's what this is saying right here. It is in equilibrium. So when you have a solid melting, it is melting and it is reforming a solid, which is the freezing point, at the same temperature. So it is said to be at a state of equilibrium. So please make sure you make a note of that. The melting and the freezing point is the same temperature. We don't think of it that way, but it is because it is in a state of equilibrium. So in general, ionic solids have a very high melting point. We learned this back in chapter 7, properties of an ionic compound. They typically have very high melting points. When we talk about a molecular compound made out of nonmetals, remember on the right side of our periodic table, they typically have a very low melting point. Obviously, when we talk about a diamond, it's around 1500 degrees Celsius, so that's extremely high. However, that's not the normal melting point for molecular solids. So I would put that into my notes. We have molecular solids, and then we have ionic solids. Very high melting points, molecular, very low, typically low. Explain why solids do not flow even though their particles are constantly moving. That's our checkpoint question. Take a second and see if you can answer that. All right, hopefully you have thought about that for a second and realize that they're constantly moving, but they're in a fixed position. So therefore, they do not flow. And that's why they have a specific volume and a specific shape. So crystal structures and unit cells. What determines the shape of a crystal? So let's talk about that for a few minutes. So let's define a crystal. A crystal is particles that are arranged in an orderly, repeating three-dimensional pattern called a crystal lattice. So please put this into your notes as well. Crystal is another vocabulary word for you right here. So I'm just going to put a box around that. And that is very similar. We talked about coordination number back in chapter 7, where you had how many different cations and anions and ionic solid around it. We mentioned a term called unit cell as well, as that's a repeating three-dimensional shape. So we're going to build on that. So a crystal is the particles that are arranged in an orderly repeating three-dimensional pattern called a crystal lattice. So here we have salt again, and we remembered its coordination number was 6, if you remember that from chapter 7. So you have this repeating property where you have no repulsion forces unless you drop it or you hit it with something which would cause it to shatter. So the ions vibrate around those fixed points inside of a crystal. And here are 7 groups or crystal systems that you can have arrangement. So please don't spend the time. I'm not going to test you on these, but you have cubic, trigonal, orthorhombic, monoclinic, and several others here that you can see, rhomboidal and that. But those are the basic crystal shapes that are going to be repeated throughout the structure, but I'm not going to have you memorize the names of them. So here's the unit cell again. We mentioned that in several chapters earlier. The smallest group of particles within a crystal that retains the geometric shape is known as the unit cell. So please make sure you get that in your notes. So the unit cell repeats. It is the repeating three-dimensional geometric shape that is in that particular solid system. So a crystal lattice is a repeating array of one of 14 kinds of unit cells. And once again, we have simple, cubic, body-centered, face-centered. I'm not going to have you memorize all of those, but these are 3 cells that can make up a cubic crystal system. Allotropes, here's a new term for you. Some substances can exist in more than one form. And the main allotrope that we have mentioned previously is carbon. So let's talk about that a little bit. Carbon is one crystalline form, a diamond, sorry, is a crystalline form of carbon. But we know there's graphite, and I mentioned earlier at the beginning of this something called Buckminster fullerenes. You might have heard of them as buckyballs. You could Google that and find out quite a bit of information. And yes, it was founded by someone named Buckminster fullerene. So we talk about the allotropes of carbon. We mentioned them. There's diamond, graphite, and Buckminster fullerenes. So diamonds, each carbon atom is bonded to 4 others in this array that makes this structure, which you've seen on my desk. I had this model for probably the last 2 months. I had it on my desk, and we were going to talk about it in this chapter, but we're doing it virtually. We have graphite, which is layers of sheets that are in hexagonal arrays. And then we have this Buckminster 60 carbon, which forms this sphere. And I mentioned how many 20 hexagons and 12 pentagon shapes are what make that up. And that's how it gets this extremely hard structure. So the physical properties of diamond, graphite, and fullerene are very different. Diamond has a high density and is very hard. Graphite is low density and slippery and has somewhat of a soft pencil lead. We can write with it. That's an example of graphite. And then the hollow cages of fullerene gives them their rigidity. Well, they're very strong too, and they're looked at a microscopic level for input of medications. Here's our term, allotrope. Diamond graphite fullerenes are allotropes of carbon. And what is an allotrope? Another definition, please get down in your notes. Two or more different molecular forms of the same element in the same physical state. They're all solids, and they have this crystal structure repeating throughout. Although the allotropes are composed of atoms of the same element, they have very different properties, and we just talked about that for carbon. Please note that not every element has an allotrope. There's only a few that we know of, carbon being one of them. We have phosphorus, sulfur, boron, and antimony. Please just be familiar with carbon. That's the one we have talked a lot about. We've mentioned oxygen previously as oxygen and O3, which is ozone. So when we talk about a solid that does not have a repeating internal makeup and property, now we're going to talk about amorphous solids. So when you talk about an amorphous solid, it does not have a structured internal makeup. Its atoms and molecules are not in an orderly array. So amorphous solid lacks an ordered internal structure. So please get this vocab term into your notes. Examples of amorphous is rubber, plastic, asphalt. Those are things that we're familiar with. They're random inside. Their arrangement is random. Another example of an amorphous is glass. Though glass a lot of times is listed as its own because it's sometimes called a supercooled liquid, So glass, I'd get that in my notes as well, is a transparent fusion product of inorganic substances that have cooled to a rigid state without crystallizing. So silicon dioxide, we talked about that previously. Sand, heated up super hot, and it gets this sort of a look that we are familiar with that's transparent and we can look through. But it is amorphous, but a lot of times it is called its own substance called a supercooled liquid. Checkpoint question. What is the difference between an amorphous solid and a crystalline solid? Think about that for a second. All right, hopefully you come up with an answer. When we talk about amorphous, remember this has no internal structures, just random. When we talk about a crystalline structure, it has a repeating unit cell. And here is what it told us about it in the PowerPoint. So you can read that through, but it's exactly how we just said. And ladies and gentlemen, that is it for the nature of solids. Key concept and some vocabulary terms that you need to have in your notes. Once again, thank you for watching lesson 13.3.